In this video, we are going to continue with matrices and systems of linear equations, and we are going to talk about how to solve any system of linear equations. And this is section 2.3 of chapter 2. Right. So suppose we have got a system of m linear equations in n unknowns, and it is given by a11x1 plus a12x2 up until a1x1 is equal to, a1nxn is equal to b1. And that's the first equation. The second equation, a21x1 plus a22x2 up until a2nxn is equal to b2. And then if we could jump to the last equation, we have am1 x1 plus am2 x2 plus amn xn is equal to bn, and we call that system 2.4, and where the coefficients a, j, and bi are constants for every row and for every column. Then we know that this system 2.4 is completely determined by its m by n coefficient matrix aij, and by the column of numbers b1, b2, b up to bn transpose. So we'll write it as a column vector. And we did mention in a previous video that the names of the unknowns, these x1s, x2, or a up to xn, or if you call them x, y, z, does not matter. What matters is the these coefficients. They are going to determine what kind of a solution we are going to get. Right. So then we have the augmented matrix or partitioned matrix 2.5. We were calling it 2.5. Will be written like this: a and then vertical slash b is equal to, so we have got all the coefficients in the system of the on the left hand side, and then we've got the right hand terms of the system on the right hand side, like that. So this is just a shorthand notation for the system 2.4, and note that every row represents an equation in the system 2.4. So if we look, for example, at the first row, it is a11, a12, a13 up to a1n b1. If you look at our first equation, it's a11 x1, a12 x2, a1n xn is equal to bn. So that's what we mean that by every row represents an equation in the system 2.4. Right. So we're going to look at an example where we have the system of equations, of linear equations, and its corresponding augmented matrix. So we are going to do the same operations on the system and on the augmented matrix, and show that we don't really need to work with the system. We can just work with the matrices to be able to find the solution that we want when solving this system. So let's look at example 2.3.1. Consider the system of linear equations with augmented matrix AB as given below. We solve the system writing down the augmented matrix corresponding to the system at each step. So in trying to solve this, the first thing we are going to do is to swap equation 1 and 3. So if you look at equation 1 and 3, if we swap it, equation 3 becomes equation 1. So now we have 2x plus 2y is equal to 6, and then we have the second equation remains unchanged, and then the third equation is the old first equation. So we've got 2y plus 3z is equal to 13. Now to write this in in matrix form, what we've just done, swapping, we can say row 1 double arrow row 3. So what this means is row 1 becomes row 3 and row 3 becomes row 1, right? And if we do the same, so if you look at this, you'll see that row 1, the new row 1 is row 3, so we now have 220 6, and then row 2 remains unchanged, and then row 3 is the old row 1, so we have 0 2 3 13. And if you look at this, this just corresponds to that, right? Then the next thing is we multiply equation 1 with half, right? So if we multiply equation 1 with half, we get, so we had 2x plus 2y is equal to 6. So therefore what it means is we are going to have 2x divided by 2, that's x. So we are going to have x plus y is equal to 3, right? And that's what we have there, x plus y is equal to 3. And to write this in shorthand for the matrix, we can say row 1 becomes, so now we don't have a double arrow because we are not interchanging, so we have one arrow going to the right, so it just means row 1 becomes half row 1, right? So therefore we had 2206, so we divide by 2, and then we get 1103, right? Now we go on to the next step. So by replacing equation 2 with equation 2 minus equation 1, we get, so if we think of equation 2 is x plus 2y plus z, right? So if we subtract equation 2 minus equation 1, we get x minus x, we get a 0 there. 2y minus y, we get a y, and then z minus 0, we get z, and then 8 minus 3, we get 5. So we get this new equation, y plus z is equal to 5. That's how we get it, right? And then if we do the same, so if we write it in shorthand, so what did we say? We said equation 2 is being replaced with by replacing equation 2 with equation 2 minus equation 1. So row 2 becomes row 2 minus row 1. So if we look at our system there, we are saying 1 minus 1, we get 0. 2 minus 1, we get 1. 1 minus 0, we get 1. And then 8 minus 5, we get 8 minus 3, we get 5. So we get 0 1 1 5, like that. And as you can see, it, whatever we have here just corresponds with what we have there, right? And then the last operation that we are going to do is by replacing equation 3 with equation 3 minus twice equation 2, we get, so if you think of equation 3, so we're saying equation 3 minus twice equation 2, so the equation 2 becomes 2y plus 2z is equal to 5. So if you say 2y minus 2y, you get a 0. If you say 3z minus 2z, you get z. And then if you say 13 minus 10, you get 3, right? So in other words, you're left with z is equal to 3, which is what we have here. And then if we write that in shorthand, what we are saying is row 3 becomes row 3 minus 2 row 2, right? So row 3 becomes row 3 minus 2 row 2, and then if we do the same, we are going to get 0 0 1 3, right? How do we get that? So if we multiply this by 2, you get 0 2 2 10, right? So 0 minus 0 0, 2 minus 2 0, 3 minus 2 1. 13 minus 10, 3. So we get 0, 0, 1, 3. Right. Now from the last equation, we can see that z is equal to 3. That is clear. Now, if we find z is equal to 3, we can then find y if we look at the second equation, right? The second equation, if we say y plus 3 is equal to 5, that means y is equal to 2, right? And then if we find y, that means we can find z from the first equation. So if we say x plus 2 is equal to 3, that means x is equal to 1. So therefore we have a unique solution. The vector x, y, z is equal to the vector 1, 2, 3. Right, so that's our unique solution. And the process can be carried out in terms of the augmented matrix corresponding to the system of equations. And this system is called Gauss elimination. So what it's saying is, whatever we did here, we can just do that on this system. And once we get to this form, we can see that we know that this is a coefficient of the last unknown. So in other words, what we are saying here is z is equal to 3. So from here, without having all this, we can do the the operations that we did and get to here, and then conclude that z is equal to 3, and then this means that x plus y is equal to 5. This means that x plus y plus 0z is equal to 3, and then from there we can solve the system, right? And this process that we did is called Gauss elimination. We are going to talk about it in a bit more detail, but that's pretty much the steps, right? And Gauss elimination comes, the name comes from the mathematician, the famous mathematician Carl Gauss, Karl, and you can Google him. He's a very famous mathematician of the 19th century. Right. Let's so for us to be able to do Gauss elimination, there's acceptable operations that can be done on a system of equations, or in this case it will be operations that can be done on an augmented matrix, and these are called elementary row operations, and we are going to talk about them. We've got 3 types. So the first one is row interchange. So if you have got 2 rows, Ri and Rj, where of course I is not equal to j, then we have Ri is interchanged with Rj, and this is the first row operation that we did in the example. So we had R1 is interchanged with R3 in the case of example 2.1.3. Right, so that is the first acceptable row operation, called an elementary row operation. Now we go on to the second one, which is called row scaling, where you multiply an ith row by a non-zero scalar. So you can't multiply by 0. So the s here is a 0. It can't be a 0, sorry. So what are we saying? What we are saying is Ri becomes SRI, where S is non-zero real number, right? And so that is the second row operation. We did that in the example. If you look at this row operation, we said R1 goes to or becomes half R1, right? And so in other words, the S in this case was equal to half. It can be a negative as long as it's a non-zero real number, that's fine, right? And then the third elementary row operation is when we add to Ri a multiple of another row. So in other words, we have got Ri goes to Ri plus Srj, right? And here we did that. This was our last operation where we said R3 goes to R3 minus 2R2, right? So here please note that there's a common mistake that is made here, where people will say Ri becomes Rj minus. It is always, that is a mistake that is very common. Please note, it's always Ri goes to or becomes Ri plus some multiple of Rj, but it's always Ri goes to Ri. It's never Ri goes to Rj here. So this third row operation, please note, Ri goes to Ri all the time, and then you can then add or subtract whatever you want here, but it's always Ri becomes Ri, right? Please note. Okay, now we've got these three elementary row operations, and what does that mean? Okay, we are going to have a definition of row equivalence. So two augmented matrices A, B, and C, D of the same size are row equivalent and written like that if the matrix AB can be transformed into matrix CD by a finite sequence of row operations. So if you do elementary row operations and you move from A to C, from AB to CD, then these two augmented matrices are called row equivalent, right? So in the example that we had, what it means is this augmented matrix is row equivalent to this one. Why? Because we transformed this one into that one using an elementary row operation. So it was 1, so it's a finite sequence of elementary row operations. 1 is finite, so therefore these two are row equivalent. If we go on to the next one, we'll see that we did an elementary row operation. This was the row scaling, and so therefore that means that this augmented matrix is row equivalent to that, because we use a finite sequence of elementary row operations. In this case, that will be 2. And if you look at this one, it's going to be row equivalent to that one also. And the same applies to this one. This is an elementary row operation. R2 goes to R2 minus R1. So therefore this is row equivalent to that, and even the previous two matrices are also row equivalent to this one, because we have a finite sequence of row operations, elementary row operations. And same applies to the last one. The first one that we started off is row equivalent to this last one, because we use a finite sequence of elementary row operations to transform the original augmented matrix into this the last augmented matrix, right? So that's what it means here. Right, now we define row echelon form. So this is definition 2.3.3 in the textbook, and it says a matrix is in row echelon form if it satisfies the following two equations. Number 1, all rows containing only zeros appear below with non-zero entries, right? So in any system, in any matrix which is in row echelon form, the rows which contain only zeros appear at the bottom of those that will have non-zero entries. Then the second condition is the first non-zero entry in any row appears in a column to the right of the first non-zero entry in any preceding row. So we are going to illustrate we are going to talk about number 2 because it seems a bit confusing, but we will try to clarify what that means. What it means is, let's look at A. So in A, we don't need to look at condition 1. Why? Because we don't have any row that has only zeros, right? So if you look at the last row here, it's 0, 0, 5. So it has non-zero entries because there is a 5 here which is non-zero. We look at that is also non-zero, that is non-zero. So therefore we don't need to look at the second condition. But let's look at the the second condition, sorry. So if you look at 2 here, there's no other row preceding it here, so the condition is satisfied. Let's look at the 2 here. So this 2 is the first non-zero entry, right, in this row, right? And if you look at its preceding row, and this is this one, you can see that this 2 will be to the right of the first non-zero entry in the preceding row, right? So it is to the right, so therefore that condition is satisfied. Now let's look at the first non-zero entry in the third row, which is our last row. If you look at 5 here is to the right of the first non-entry in the preceding row. So in this row, the first non-entry is 2, so you can see that 5 is to the right of 2, and this in the first row again we've got 2, and it's again to the and then 5 is also to the right of this 2, right? So that's that. Same story with B. You see that with B we have the row containing all zeros is at the bottom, so that's fine. If we look at 2, there's nothing preceding it, so that's fine. There's no row preceding this row. And then if we look at the second row, we'll see that if we look at the first row, this first non-zero is to the right of the 2, right? And then if we go on to 3, we'll see that the first non-zero in the third one is 3, and it's to the right of 2, and it's to the right of it's to the right of 1 in the second row, and then it's to the right of 2, right? Let's look at C. C, we've got zeros at the bottom, so that's fine. All the non-zero entries are at the top of this one, so that's fine. And if we look at this second row, we see that 2 is to the right of 1, and then 5 is to the right of 2, and 5 is to the right of 1, so that's fine. So these 3 matrices are in row echelon form. Let's go on to ones that are not and give reasons why they are not. So let's look at P. So for P, we can see that we have got a row of zeros at the top, so that So condition 1 is not satisfied because this rows, sorry, the row of zeros is at the top of, it's not below the ones that are non-zeros. So this is not in row echelon form. Let's look at Q. So for Q, condition 1 is satisfied. Why? Because we've got 0. The row of zeros is at the bottom. If we look at the third row, we'll see that the non-zero first entry of row 3 is 3 here, and it's to the right of 3, so that's fine. Right, now let's look at the row 2. If we look at row 2, we'll notice that row 2 is the first non-zero entry is 3, and it is not to the right of the first entry of row 1, right? It is directly on top, so it's not to the right. So if it was proper, we would have a 0 here and then a 1 there, a non-zero value here, right? And then we could say that that value is to the right. But here we can see that it's directly on top of the first non-zero entry in the first row, right? So that is the problem. So that's why it's not in row echelon form. Let's go on to R. With R, the zeros are at the bottom, so that's fine. Then if we look at row 3, we can see that it is not to the right of this 3 is not to the right of the first entry of row 2, the first non-zero entry of row 2. It is directly on top, so therefore that means that it is not in row echelon form because it is not to the right of the of row 2, right? So that is the reason, right? Okay, so we are going to continue on this in the next video, where we are going to see how we can use Gauss elimination to get to row echelon form and then solve the systems. Just another example. So you see that when we solved this system in example 2.1.3, we started off with that and we ended up with this system, which is row equivalent to the original system. And you can see that if you look at this matrix, it is in row echelon form because we don't have 0 as a row of zeros, right? So the first condition is satisfied because we don't have the row of zeros. And then if you look at the second row, it is to the right of the first row non-zero entry. And then if you look at the third row, this one is to the right of this one, and therefore it is in row echelon form. So once a system is in row echelon form, we are able to find the solution of a system. That's what we are going to then talk about in the next video. Thank you.